Right, we're on.
Okay, we are indeed live. Brilliant. Okay, yeah, another exciting DDD session. At least I hope it's going to be interesting, exciting. Just a reminder, if I can actually find my mouse and click the button. Come on, there we go. We have a code of conduct. It's all very straightforward, but please be aware of others. Be friendly and patient. I mean, one of the hallmarks of DDD events is how friendly they are, how welcoming they are, but also we want to be respectful. Lots of questions and viewpoints, but that's a good thing. That's what this is all about, as are being understanding of differences and considerate to others. And the link there is on the side for you, the terms of contact. DDD being virtual hasn't taken sponsorship directly, but what we have done is we've been fundraising for the National Museum of Computing, which does a brilliant job in preserving our computing heritage all the way back. And if you want to give, use the fundraising link there, it'll be much appreciated. We have in fact had sponsors who have given to that charity, and we're really grateful for the support that they give both in the real events in the real world and supporting this virtual event to make sure it's a good success. Finally, social media. Use the hashtag DDD2020 or CC at Developer Day, and we'll have a really great conversation on Twitter. But enjoy the day. Right. Get rid of that, and we're on to the session. Solving the travelling surveyor problem. Really catchy title, this one. So a quick introduction. My name is Joel Hammond-Turner. I'm technical lead at Landmark. I've been doing DDD style events for about 6 or 7 years now. I've been working in the industry for, it says 15, it's probably more like 20 plus now years. And I really enjoy taking my passion for the technology, finding interesting things to present at these sort of conferences to make you think, give you some ideas, maybe show you something new. As I mentioned, I worked for Landmark. Landmark was originally known just for doing digital maps. Now we're a true prop tech, legal tech and enviro tech innovator. Fundamentally, if there's anything to do with property data and land data in the UK markets, we're involved somewhere. And we're on a big transition to be a unified single company covering the whole property transaction, both commercial and residential life cycles. Now, part of that is where we came in with the problem that we're going to look at today and why Google OR Tools is a useful solution. LVS, Landmark Valuation Services, is all about providing the tools that surveying companies use to get your survey when you buy a house done, sent back to your mortgage lender, approved, so your sale goes through. They provide an end-to-end residential property transaction lifecycle management system. And that's what I've worked on for the past 5 years, up until probably the middle of the year. Part of that is a product called Valuation Hub. This is what surveying companies use to manage the surveys. It's quite a big, complicated system. It's got 40 or 50 components, a lot of it's in Azure. And a spoiler for what we're going to look at later on, all of the bit we're looking at in terms of this routing problem is in Azure. Let's take it all the way back now. Let's take it back to the travelling surveyor problem itself. What is it? Well, hopefully everyone knows it. Though possibly you don't know quite how old conceptually it is and quite how complicated it can be. So this was actually formulated originally in the early 1800s by Hamilton, and is properly called a Hamiltonian cycle problem. It's very simple. Given a travelling salesperson, that was originally couched in terms of graph nodes, what is the shortest route to travel through all the nodes on the route and return to the beginning? Hence Hamiltonian cycle, going around in a circle. And what's interesting about it is it's actually quite difficult, because as the number of nodes expands, the problem becomes much, much harder. And the first few solutions, one of the earliest ones is called nearest neighbour, aren't actually very good. In the 1930s, it was mathematically proved that the nearest neighbour was in fact definitely not optimal. It must always give a non-optimal solution. It's up to about 50% longer nearest neighbour than optimal solutions on any arbitrary set. And it's been looked at all the way through right till the 2000s, because actually the problem is not just about people moving around in the real world, but network transactions. If you want to use a computer-aided CNC machine, the paths that the CNC head needs to take cover that. Microchip manufacture, circuit board manufacture, all of these actually come down to some sort of travelling salesman problem. It's actually really ubiquitous, surprisingly so. Because it's ubiquitous and because it's been around for such a long time, there's a lot of solutions. These are just the ones that are referenced off that Wikipedia page. And these solutions have very hard limits. Interestingly, the brute force, it's a exponential problem. It means that over about 15 or 20 cities, it's unrealistic to calculate. Some of the early exact algorithms, you'll see, have got limits of 75 to 100, and the very best one can only just do under 90,000 cities, which sounds like an awful lot, but when you're dealing with something like a CPU layout problem, you're dealing with tens of millions of cities, quotes, in terms of the transistors that you're going to route onto that CPU die. So there's been a lot of work over the years about how to provide solutions, both exact ones and then approximate ones, because most of the time you don't actually need to have the very fastest algorithm. You just have to one that is fast enough. And these heuristic algorithms give you that fast enough and accurate enough balance. The most interesting one that I found before last night is one called Ant Colony, where it is literally they simulate how ants leave pheromone trails to come up with a approximation for the travelling salesman problem. And a friend of mine on Twitter last night, when I was doing this, had found some really recent research, which I've not linked yet, about someone simulating bacterial growth to do the travelling salesman problem. And weirdly, it works, and it's really efficient. I'll try and find a link for that and put it in the notes later. So there's lots of ways to do it. There are so many ways to skin this cat. But we've only got a few surveyors. It's simple. You know, surveyor needs to go to a job, needs to come home. How hard can it be? Well, yes and no. This is the real world. And even a supposedly simple requirement like that can be slightly complicated. So going back to right back to 2007, I looked it up. the original requirement for in Valuation Hub, a survey booker being able to book a survey for a surveyor to go and survey someone's house was described like this. Very, very traditional as a I want so that. But there's a couple of really nasty little details in there that make this much, much more complicated than it looks initially. To put it into perspective, the work to do to meet this requirement took a team of 5 people 6 months. And we'll see why. Like I said, there's detail here. The first thing you can do, I always tell people to do this, I had to bring it back, was to look at a person, what actually happens. So this is how a real booker would really book. There's some phone conversations with estate agents, they're checking opening times, they know where the location is, and then she's given a suggested slot to book that provisional appointment for one of the staff surveyors. And all those words and details there give us some requirements that are expanding out. So the first one here is, for any given job, there are many surveyors who could do it. So immediately we're not dealing with one Hamiltonian cycle, we're dealing with one per surveyor. Take it a step. And the other parties, they don't have the same work patterns. Some may work some days, some may work others. They've got targets, they've got points, they can't do certain jobs. All these require some thought. You don't have to do the survey tomorrow. In fact, more often than not, you can't. But you do need it done as soon as possible because the mortgage companies want that information as quickly as possible, and the seller and the buyer want it as quick as possible so that they can complete as quickly as possible. No point in waiting around weeks and weeks for a survey to be done. Surveyors are, well, I won't say they're a lazy lot, but who wouldn't want to minimise their drive times? They really don't want to drive 2.5 hours to do a 15-minute survey. That's just unrealistic and unfair. And likewise, if there's 2 people who can do the job equally, and when the distances are near enough, would you always give it to one person so someone else has no work? You need to share the work out fairly. And we said, devil's in the detail. You need to handle key collections, drop-offs. And it's more than one just appointment in a day as well. And the estate agents have opening hours. So you have to be at the estate agents during the opening hours to collect the key, to do the job, and then you may or may not be able to drop the keys back through the door, or you may have to be back at the estate agents to give the keys back during opening hours. So time is now a factor. The arrival time at each appointment and at each location becomes a factor. And finally, I'm sure all of you have had phone conversations. Yes, we'd like to come and look at your house. We'd like to do your boiler. Your package will be delivered. Have you noticed how no one ever tells you exactly what time until usually just before? Case in point, last Sunday morning, I got a text at 7:30 a.m. telling me that my package would be delivered by between 7:45 and 8:30. It was delivered at 7:45 before I'd even woken up. But why are they saying it's so late? Well, that's because they want the flexibility to reorganize. This is another requirement of this kind of problem. You need to be able to shuffle, potentially shuffle between surveyors in this scenario, certainly shuffle times of appointments during the day to optimize the route. And then this particular requirement, one of the biggest surveying companies in the country, they've got hundreds of surveyors covering the country. They've got thousands of jobs booked in every day, and they want to plan a month in advance, up to a month in advance. They need to know what their capacity is. They need to know what's going on. So this is a complex n-dimensional routing problem. By n-dimensional, I mean there is not 1, 2, or 3 dimensions of problem, but many, and potentially very many dimensions of problem. So just from that little piece of work, description about the problem, going from Hayley's description of how she works, looking at the requirements, we've got all these dimensions. Surveyors and their shifts, where they start, where they end, points, any restrictions, windows and ETAs, distances and times, key pickup and drop off, they all add to the complexity. They are all the problem constraints. And that's ultimately where we go with this. We have a problem. We have some constraints on that problem. We want to solve and optimize that problem. So that's the background. That's where we got to the start of this piece of work. We did a load of research on how to do this. We looked at, can we write our own algorithms? And we decided that's far too much like hard work, and we don't have any PhDs in maths in the company. So let's find some off-the-shelf tools that we can use. And we picked on this tool, Google OR tools. Now, I'm still not entirely sure what the OR exactly stands for because it seems to change. It seems to be optimization and routing in some documentation. It seems to be optimization research in others. The URL, definitely optimization involved because that's in the URL. What's it all about? It's software tools, a tool set, a library for doing routing, scheduling, as I say, packing, assigning, solving. It's actually really big and really complicated. And we ended up using only one comparatively small part of it. What the library toolset gives you is an open source optimization library. It's cross-platform, runs on all the big platforms, and they've done some very fast native libraries for the major platforms. If you haven't got the major your platform covered by that directly, for some reason you want to run it on ARM, on a Raspberry Pi or on an Edge node, you'll probably have to build the native bindings yourself. I'm pretty sure someone out there has. I haven't looked. Multiple language bindings. There's no particular requirement to use any language. Most of their samples are in Python because these are data scientists who are creating, maintaining and running these. Excuse me. And it supports multiple solvers. So as well as the normal solvers that you get, you can have third-party solvers. So if you don't like what Google's given you, that's fine. You can go and use someone else's. Right. So that's the basics of what it gives. And I mentioned solvers. It comes with a load of them by itself. So it covers a whole gamut of problem optimization and solution. And we've got some really great names. I mean, the GLOT solver, the SKIP solver. The CP SAT solver is a bit boring, but the one I really like best is the bin packing solver. How much stuff can you get into a bin? And there is an algorithm called the knapsack algorithm, and that's the one that they implement. It's got a really broad range of capabilities. What we care about is actually the routing solver, and that's the constraint route solver, and that's what we ended up using. If you want to actually get started with it, it's really actually very easy. You install the Google OR Tools package, and everything you need is there, and there's C# samples on their website which make it really easy to get started, which is exactly what I did when preparing this session. New project, install the package, define your problem, configure the solver, run the problem and print the results. It was really very simple to get that first one working. What's a bit of a problem though? It was actually really slow. Now remember I mentioned they've got native libraries. That's absolutely critical, and we'll see that in a second. I've got a demo. If you don't install the native binary package as well as the wrapper package, the application runs extremely slowly, which basically confused me for 2 to 3 days until I realized I actually needed to install that, and then it ran in a sensible time frame. So let's now try and jump over to the console and Visual Studio Code and actually have a look at that simplest TSP, traveling salesperson problem. So I'm going to run up, PowerShell first, and I have a pre-prepared demo, O1 simplest case, and I will .NET run it. So first thing to note, yes, I've got warnings because their packages don't actually support .NET Core yet, which is a shame, but it works just fine. And I developed all this actually on a Mac. So you can see here, I've said, tell me the shortest route to go from New York and back again via Boston, Chicago, Minneapolis, etc., etc. That's the very simplest, straightforward traveling salesperson example. So let's have a look at how we implemented that. Now jump to Visual Studio Code. All this code is available on a repo. The link will be at the end on the last slide, so you can have a look at it and play with it yourself. And as I said in the slide before, it's very simple. You define your problem. I've stuck that in a class to make it simpler. You set up a routing model. You define constraints. And then, finally down here, you solve with the parameters. And then you print a solution. There's not a lot of code here for what it's doing. So let's first look at the problem. In this case, actually, the problem model is really defined by the matrix. This is traveling salesperson. So these are the distances from node 0, New York, to node 1, from New York to node 2, New York to node 3, and so on, likewise, backwards. So it's just a distance matrix, very simple. I could have just printed integers for which city we're in, city 1, 2, 3, 4, 5. I've got a little enumeration just to give the cities a name. And we say, because this is traveling salesman, we have a vehicle, because the constraint route solver generally thinks in terms of vehicles. And we're starting from New York. The depot is in New York. That's where we start from. That's where we return to. So that's the problem model, straightforward. The rest of all this code is setting up OR tools to run it. OR tools thinks in terms of lots of arrays of ints. Everything is arrays of ints, where ints are references, not pointers, really, just array references, and they are all over the point. So here we're saying, use this helper class to manage the indices of however many distances we've got, by how many cities, and how many vehicles, and define the route city as 0, as New York. We then pass this to the routing manager. This is effectively the constraint route solver. It's the engine that runs it. Now, the whole purpose of the TSP is we want to minimize the distance between that we're traveling. So we need to do 2 things. For every arc between nodes, we need to define what that distance is. And you'll find you end up doing quite a lot of this code, because the engine will give you an index that you have to, which is within its own construct, that you then have to translate into your set of data. The node is effectively the number of our city, and then we use that, in this case, to peek into our distance matrix to get the distance between the two cities. And this callback gets called a lot. We'll see when we run it just how much. So we register this transit callback. It's a callback that's run every time the algorithm transits between two nodes when it's making its considerations. That doesn't actually constrain the problem. It just defines a value that can be returned. The TSP, not the bank, describes the problem as I want to minimize the cost of a route where the cost is the total distance. So this helper, set arc cost evaluator, says when you're evaluating the cost of a vehicle moving on between two nodes on an arc, use this callback, or actually this callback. But because everything is not quite pointer based, reference based, you need to take the index that the register method gave you and pass it into here. So at that point, we've actually got the constraint applied. We then set up some options for the solver. One of the nice things is there are plenty of different values of ways to tweak how the solver works. And when you're looking at using this, you actually need to try each one, because they do give subtly different details. Fortunately, there's an automatic setting which says, I don't know, take a guess. And that's always a good place to start. So in this case, we've gone, use the automatic solution. I'm just wrapped this in a little textual spinner. Here's where we actually run the solver. Go away. Here's where we actually run the solver. And we get a solution that we then print. The last part of this code is overly complicated because, as I mentioned, everything's by indexes. So your solution here is actually an array of values for the arcs for each node. And so you end up having to ask the routing manager, sorry, the routing algorithm, what is your route? What was the route you chose as your solution? Separately from the solution that it returns you, because the solution is just the array of values that are the distances, as opposed to what the arcs are and the values. It's a bit complicated. Ultimately, we iterate the route, we get the solution values, gives us an index that we then look up to go from and to, and you'll end up, this code becomes boilerplate all over the place. And that lets us write city to node. Great. So we saw that working here, and it took 0.8 of a second to run that. And it should take about 0.8 of a second again, 0.72. I mentioned this is without the WinX64 runtime package. We chuck that in. Well, no way PowerShell thinks it takes so long to clear the screen, and run that again a couple of times. We should see it be even faster, because this is a really simple TSP problem. That took longer. And it's decided it's going to actually increase, which is great, because Last time I did this, it knocked a factor of 10 off it. It might be something else on my system causing problems. So that's my first demo fail of the day. Brilliant. I didn't sacrifice enough chickens. Okay, let's go back to the slides. Just check where we are. We are 30 minutes in, 15 to go. Okay, so I've got the side here. We saw distance matrices. This is actually quite important. For routing problems, you need to know what your distances are and also your times. And there's quite a lot of ways of doing it. For flat plane problems, Pythagoras. For city driving, there's what's called the Manhattan or the taxi driver distance. If you're doing flights around the world, aircraft, you have to use the Great Circle distance. And for navigation around on a driving from A to B, Google actually has a distance API, which is really good because it doesn't just tell you the distance, and that's not as the crow flies, that's actually on the roads around there, but it tells you the time, the duration, based on average traffic patterns. So if you're routing people, that's really, really useful. There's a problem. It actually costs some money, which is quite irritating, because if you haven't got a Google Enterprise license, that data, calculating it on the fly, becomes really, really difficult, really, really expensive. I meant to show you the debug outputs. I should have printed it rather than debugging it. But you can see it iterates hundreds and hundreds of times just for a very small 5-problem solution. So I had a quick demo of multi-vehicle routing. All that really did is have a slightly different data set and a more than one vehicle. So let's just quickly go to my console. I'm not going to show the code because it's pretty much exactly the same, with the exception that the print method has to actually print out, has to iterate 4 solutions. So I've said, let's do 4 vehicles. You saw that it's solved 4 vehicles running the TSP in near enough the same amount of time. That's where the power of the OR system is. It can scale out across multiple vehicles, surveyors, whichever, very easily, very quickly. This, of course, has no constraints over who does what. It's just, I want you to go, I want between the 4 of you to go to all these places and come back. It's a very simple solution. Okay, pushing on, and I've kind of glossed over that one because we're a little tight for time. So in our scenario, we have to recommend a surveyor. So we calculate a TSP route for the current surveyor, for each surveyor that we've set as a candidate, because some of those constraints we pre-filter. Calculate the route for the current schedule on any given day, and we'd have to do that for 5-10 days in advance. When we're learning how to do that, Google Maps is definitely a friend. Then we have to calculate the TSP route for that surveyor on that day with the additional route heading. And then we see the difference. In this case, it's an additional 3 minutes on his day, on his travel time. And we repeat, and we find the best surveyor out of all the surveyors and all the days. What's the one with the least change in distance and time? So that's the problem we were actually solving. There's some niceties to do with when you arrive at places, but that's those requirements really getting extended. And when we're developing this, to understand this, we found it was really, really hard, significantly hard, to define these problems. Now, how do we prove that our routing engine was working unless we knew base data, what we expect, does it actually do what we think it's doing? And those problems are really hard to define when all they are is a bunch of integers in a bunch of arrays. Google OR's tools is this really thin wrapper over C++. Everything is an array. Nodes, an array of int. Vehicles, an array of int. Solutions are an array of int. Evaluators, an array of func of int. Dimensions, yeah, you get where I'm going with this. Everything is an int. And a lot of it is hidden and internal and quite hard to find within the OR engine, because it's actually designed to be really tightly bound and small. I mentioned it goes onto edge devices very easily. It's really, really hard to explain your problem in a very simple way. You end up having huge arrays of things that, unless you understand exactly what's going on, you can't define the problem. Certainly your business owners found it really, or our business owners found it impossible to understand what this particular test or proof meant, because it's a load of integers. Writing tests, writing problems, defining problems with the tools is actually really pretty hard. Once you've done it, that's fine, but there's a confidence problem here. How can you be, and how can you prove to your business that this tool is useful, accurate, working? And hence for DSL, which is what we did, and what I've to some extent re-implemented in some of the demo code. By defining your problem with a domain-specific language, it makes it very, very easy then to define tests. What happens when I add this person, he's got these particular appointments at this time on these days, and I ask the system, can you do this work? When should he do this work? When does it appear? So we defined a DSL as actually a bunch of extension methods on some domain classes. And that let us do exactly what's on the screen here. We can say, let's have a new problem. Bob has a shift when he works between 9 and 5. So that's straightforward. That's actually going to be part of the constraint on the surveyor. It's, well, he's not going to leave home until 9 AM. And he's happy to work, but wants to be home, or at least heading home, by 5. So we need to make sure that his jobs can fit within that time window. And likewise, actually, the vehicle route is actually what you're calculating. So we've got a vehicle route for Bob. That route is only valid within his shift. Where does he leave from, and does he go back home? Because one of the detailed requirements was actually on a Tuesday, Bob will not start from home because he's dropping the kids off at school. So he starts from a totally different postcode, but goes home at the end of the day, or vice versa. We need to define what these appointments are, and where has he got to be and when. We kind of glossed over the when part, and we'll gloss over the when part in the code as well, because that's really difficult. Solvable, but difficult. Then we've got to say, he has an appointment at some time in the morning to be at this postcode. His appointment to be at another postcode, also sometime in the morning. Or, more likely, and actually the businesses will tend to want to define and give customers that, oh yes, he'll be there on Tuesday. Because that gives more flexibility to the business to actually adjust these timescales. So we need to define a working DSL for that. I thought I'd do a really good job. I couldn't take the exact code from our production environment because it's a little bit specific and it's didn't really demonstrate quite what I wanted. So I created a working DSL for Google OR tools, and that's in the sample repo. Except I kind of bit off a little more than I could chew, and it doesn't quite work yet. Sorry about that. I will get to it and fix it. I spent, let's say, 2 days wondering why it was slow until I put in the native wrapper, which then got rid of a whole load of problems because it was actually solving things. So the code, just to give a flavour for it, but only going to do it for 2 minutes. So in here, in our Fluent API, we define, not the tests, but the API, we define our extension methods. So, to create a vehicle route for a vehicle called Bob. We take our problem, we add a vehicle, we add a route for that vehicle. And part of the nuances of OR tools is you tend to have to push those indexes around the place a lot. And in order to hold the indexes, you end up using a load of tuples. That's one of the reasons I didn't like our production code, because it's full of tuples everywhere. So all I've done is I've defined this problem vehicle pair, which happens to be a tuple of a vehicle and a problem. And that then gives us a nice extensible API. So when we say the vehicle is leaving from, you can take a problem vehicle pair and a problem route pair, because a vehicle is a route. Naming is interchangeable in a lot of cases. The actual vehicle class is used to get the index, and I say the route starts at this postcode. And we can define shifts, and we can add appointments. And so this then means when we actually define the problem, where I do here in my recommendation model, on the create method, I use exactly that code. Here's Bob's shift. Here's Bob's route. Add appointment, existing appointments to the route. Do the same for Eric. And then, as we said before, in the recommendation engine down here, we just iterate all the vehicles, all the surveyors. We get the routes. We get the route for that particular vehicle. We calculate an initial solution. And we calculate an updated solution by adding on the new appointment. And round we go. Okay, when we start closing this out. So we implemented all that. We implemented that, the DSL. We're able to use that to define our tests to prove the tools work right. And we actually also used it as the mechanism to translate from our internal representation of the data into the problem for the OR tools. Into production. As I gave spoilers at the front, that's all Azure. And it's actually fairly straightforward. We have a bunch of Azure functions that exercise the OR tools. I mentioned our postcode travel time data. That we bought in. We looked at using Google, but ultimately, because of the API costs, it was cheaper to go in and pay an annual subscription to a data provider who gave us 50 million rows of travel time data throughout the UK that we update about quarterly. We didn't really need the granularity of Google being able to say, well, actually, you're doing this route at 9 AM as opposed to 3 PM, and the travel times would be different, because it wasn't that far off. The postcode data providers was averaged out and was reasonable. So we've got 50 million rows in a SQL Server database in Azure, and our data services team manage that. We've got a Cosmos DB that we record every single recommendation that any of these functions make. So every time someone says, here's a new appointment, who can do it, all the results gets put in Cosmos DB. That would seem to be really, really excessive, but it's not, because there's a third party here. There's the actual surveying company. They have equally had little trust, and rightly so, because it's brand new stuff, in what the recommendations were doing. And also they tend to tweak and all the constraints quite a lot, and they change surveyors how far they can go when they work. And they kept on, right from day one, as we expected, kept asking questions. Why has the system recommended this? Why has it recommended that? Why not this one? By recording every recommendation, we're actually able to go back, look, see the data, and say, it recommended that because it was half a mile shorter, even though you didn't expect it to be. The actual engine hosted in Azure Functions. One thing to note, I don't know whether it's changed, I already ought to check. Azure Functions by default run in 32 bits. So you have to put it into 64-bit mode, and the Google OR Tools library is a 64-bit library. So you need to do that. That actually has a cost implication because 64-bit functions cost 1.5 times or so more than 32-bit functions. And we fronted it with API management because we're good security-minded people. So what's that given us? That's given us 1,000 cases an hour, 50 bookers, one every 4 minutes. It's given us, on average, 2 to 4 surveyors suggested per case, or who could do each case, which were the 5-day cases and 6 cases a day. That gives us between 10 and 40 surveyor day combinations for every job. $1,000 cases an hour. That's 10 appointments a day, 120 nodes per solution. That's 10,000 function calls a day at 10 seconds a call. These are actually fairly expensive functions to run, but it's a difficult, complex problem. I would not have wanted to try and scale this out in any other way in an on-prem or VM-based solution. And it's there, and it's been running for 3 years, and it runs the surveying company, the largest surveying company in the UK, and it is used all the time. And it's actually been really, really successful. And it will be rolled out to loads of other scenarios because the learnings we've got from this give us a huge capability in the optimization space. I'm slightly over 2 minutes according to my clock. So to wrap up, what we've seen, what have I tried to show you? What I've tried to show you. Scheduling jobs for surveyors can be hard. Problems can look really simple, but when you actually start layering on the requirements and the constraints, the problem space becomes n-dimensional, where n is quite a large number. Going back to requirements, understanding the problem, breaking it right down, making sure your business understands why you're doing this is really the problem, and actually defining optimal. I skirted over the how do we define optimal. It isn't necessarily just the shortest or the quickest. OR tools let you define costs for a lot of things, and you can train your optimizer, teach your optimizer to optimize against lots of costs. Ultimately, it's just maths working in integers, but you have to define that problem very carefully. OR tools are the solvers. They are fast. They're actually really fast. On this old machine I'm running on, they don't look it, but if you think about problem size it's solving in Azure in the production environment, that's actually quite not a big problem there, because that's solving 200 cases in advance. Do calculate your distance and time data up front. That's going to be the biggest time to work it, because it's being iterated all the time. Yeah, these are the references, your distance time data, and this scenario is the one that gets hit hundreds of thousands of times each time you do a run like that. But because the API is really slim, do define a DSL, because otherwise your tests, defining problems, it just becomes a real headache, and writing unit tests is nigh on impossible. DSL then make that viable and sensible and easy. And like I said, users want to understand the recommendations, do save them. Okay, I've covered it all. That's everything I wanted to say. I'm sorry I have a broken demo. I will make sure that gets fixed and updated as I go on. My contact details are here. I'm happy to chat after this or online. You can find all my details here. The repo is at bit.ly ORTools samples, and the slide deck is at bit.ly ORTools deck. I want to thank you very much for listening, and I'll take any questions now. And PowerPoint balked me again. Can't see any questions on the chat. It's all been very quiet. Okay. Well, if there are any questions, I'll bring this to a close. Well, thank you again. Thanks to our sponsors. Thanks to Boss and everyone for organising this. And let's enjoy the rest of DDD. Thank you very much.